Um, so today I will talk about a loss function that I've developed over the last couple of months, and I'm very excited about this project and also to hear about what you think about this. And you see in the title, there are some words that may seem unfamiliar to you, like add boost. I guess you all know what regularization is in neural network. But if you don't know what add boost is, don't worry, I'll introduce that to you. But to start off, let's start with a motivation. And then particularly, I'm interested in when you train a classifier model and LLM is a classifier, what loss function do you typically use? Does somebody want to make a suggestion? You can just unmute yourself and say something. Okay, people are a bit shy.
Cross
And then
entropy
cross
from my
entropy.
side. Yes.
Yes, cross entropy. That's what I wanted to hear. So most people use cross entropy, and then sometimes they will add something to that, like a penalty for label smoothing or something similar. And my goal of today is to have you not do that anymore, to use a different loss, or at least to consider using a different loss. And that different loss will be panics. This is the one I will be presenting to you today. So hopefully I will do a good job and convince you that panics is a good alternative. But we'll have to do a detour and first talk about AdaBoost. It may seem this has nothing to do with loss functions, but I guarantee you that the pieces will fall into place and you will all see why I did this detour. Because AdaBoost is an ensemble learning technique. And what is central to all of ensemble learning is the concept of a weak learner. This concept comes from probably approximately correct learning. And intuitively, what it means is it's a machine learning model that performs just barely better than guessing. For instance, you want to classify whether someone has a disease or not, and then it will give you something like if you're older than 60 years old, you have the disease, otherwise, you don't have it. So, this is what these decision stumps do. And we can see that this will not have a very good performance, but it's better than flipping a coin, and that's all that matters. Now, what we would like to have, of course, is a strong learner. And the way we will achieve this is by taking a linear combination over many of these weak learners. These can be hundreds or even thousands. And now the question is, how do we fit these, right? It seems a bit intractable. And the way that boosting and also AdaBoost goes about this is via a greedy optimization. So here again, we have in purple the strong learner, which is this linear combination of weak learners, GI, and then the GI, they greedily minimize an exponential loss function. This is important. So we'll come back to the exponential loss function later. And we see that it seems to be quite aggressive, right? It's exponential, meaning that if the true label is, for example, 1, and now f is very negative and large in magnitude, then it will explode. So this is for binary classification. And actually, AdaBoost was not derived like that. It was not meant to minimize the exponential loss. It was derived in a different way, but they figured this out later. And when they figured it out, they were confused that it works at all because in real world data, we have lots of noise. And so it doesn't seem plausible that we should have this exponential penalty on uh, great mistakes. And even crazier, it seems like that we can keep adding these weak learners and the model keeps getting better at generalization. And Leo Breiman, famous scientist in the early days of machine learning, he went as far as to say that AdaBoost with these decision trees is the best off-the-shelf classifier in the world. So what I really wanted to do in this project is to find out what is the secret sauce of AdaBoost, what is the magic, and how can we translate this generalizable, this regularizing effect that it seems to have to training deep neural networks. But before we get into what our specific contribution is, I would like to point out that there has been uh, an extension of AdaBoost to the multi-class setting. This was in 2009. So we can't only do this with binary labels, but we can also have as many labels, as many classes as we want. So here we have k different classes. And now we don't only have one single f, but we have one f for each class. You can think of these as logits. In neural networks, we call these logits, and I will also keep using this term from now on. And so what happens here is that we rescale a bit these logits, and then we also have a zero-sum constraint on the right. Now you may ask yourself the question, why do we need this, right? Why not just only have the exponential loss? Turns out if we only have the exponential loss, then all the logits will go to infinity because there's nothing keeping them back. We can just arbitrarily minimize this and we will keep improving on the loss. So that's why here we have this zero-sum constraint. But anyone who's ever tried to do constraint optimization with neural networks knows that it's very painful to do that, and you want to avoid constraints at all costs. And so here comes the central slide. We developed a new version of the multi-class exponential loss, and this one does not have constraints. Again, we have this exponential loss part, but now we also have a penalty, and we see that it does something similar. So it also tries to prevent these logits from going to infinity by penalizing them for being large. Now, does this work at all? The answer is yes, and it works very well. Here we have an experiment with Cypher 100. When we use cross entropy as a training loss, we get this typical phenomenon where first validation score improves, so larger is better here, improves, and then at some point it becomes worse again. And label smoothing is one way of dealing with that. So we see with the orange line, we get a bit better generalization, but then we level out, we don't improve further. And with PenX, we see this phenomenon that we also observe in AdaBoost. We keep training for many epochs, and it just keeps improving in terms of generalization. Now, this is not only true for Cypher 100, we also try it out on various other data sets, and we often get the best performance. Of course, we're only comparing here to methods that are similar in terms of computational demands. Now, you may wonder what's happening under the hood. Why does this work at all? And we believe that the key to this generalization ability lies in an implicit margin maximization. So what is a margin? Margin, you can think of the distance of data points to the decision boundary. Now, when we train a neural network with cross-entropy loss, then often this decision boundary gets very close to data points. And with PenX, similarly to a support vector machine, it tries to keep the decision boundary away from the data points. And one can show theoretically that maximizing margins gives you guarantees on generalization. So this is really what's going on under the hood. I personally believe that it's important that when we develop new methodologies that they're theoretically grounded. And so we also have some theoretical results for PenX. The first property that PenX fulfills is called Fisher consistency, and it is very simple. We can just describe this in a single sentence. When applied to the whole population, the derived statistic should be equal to the parameter. So what does that mean for PenX? PenX, we want to minimize this empirical expectation over this term in there. And now what we do is that we replace the empirical expectation by the true expectation. And now we can minimize this with respect to f, the logits, and then we get f star. And now what is the parameter of interest? We would say it's the Bayes optimal classifier, right? This is the best we can hope for. And it turns out that we do recover the Bayes optimal classifier. So this is the true probability of y given x in the following way. So this is just a softmax of the logits we got from minimizing the loss with a slight rescaling of the temperature. And interestingly, many regularizers actually fail this Fisher consistency. So the regularizers you may be familiar with, they look like this. We have cross entropy plus something, and this encompasses L2 regularization, label smoothing, confidence penalty. And the intuition for this is that the cross entropy loss itself is Fisher consistent, and then the penalty pushes us away from the Bayes optimal classifier. I already showed you in this toy example that PenX maximizes margins. We can also prove that it does that. Here we define the margin of an example, xy, as the difference between the true logit to any false logit. I think it's easy to see that we want this to be large. And indeed, we can show that the probability of the margin being small is small if the Penix loss is small in expectation. Now, I started with this ADA boost, and it seems like what I did was just introduce a loss function. There's nothing about ensemble learning. However, we also have a result that connects performing gradient descent on Penix, that connects it with ensemble learning with ADA boost. You may have heard of a generalization of ADA boost called gradient boosting. Here you can pick an arbitrary loss function and then you minimize that. So what you really do is that you project the gradient onto these weak learners. And we also have a result that shows that we can go the other way. So when we perform gradient descent on the Penix loss, we recover an implicit form of ADA boost in some limit. And without going much into details, I just want to provide you the intuition. And we recall that AdaBoost takes a linear combination of weak learners. And when we do a first order Taylor approximation of a neural network, then we see that actually it is doing something very similar. When we perform a gradient descent step, then we can assume it is additive as this eta parameter goes to 0. And it makes sense intuitively. For example, when you randomly initialize a neural network and then you perform a single gradient descent step, that is a lot like a weak learner because this model will perform not very well, but just a tiny bit better than not performing this one gradient descent step. And then the key lies in performing many different gradient descent steps. And this is how we get a strong neural network. Yes, now I would like to point out some limitations in the future work. Uh, One limitation is that we observe that training with this loss can be a bit unstable for large data sets and large models. Then Panix is often compared to hard margin SVMs. It is not really doing the same thing, but there are similarities to hard margin SVMs. And one may wonder whether we can derive a soft margin version of Panix also, just like there are soft margin versions of support vector machine. And finally, I'm curious to discover opportunities of Panix for fine-tuning of large language models. So I think we have a lot of junior researchers and PhD students here right now. So I'd be interested in co-supervising you, perhaps with Zhijing, on a project where we discover how and whether we can apply Panix to fine-tuning of large language models. And with that, I would like to conclude. Here are 4 key takeaways. The first key takeaway is that we can translate the AdaBoost magic to training deep neural networks, and this we do via PenX. The second point is regularization is not at odds with Fisher consistency. In other words, you can actually bake generalization into your loss. Your loss does not need to look like cross entropy plus a penalty. The third point is PenX implicitly maximizes margins, and this is the main reason for why it generalizes well. And finally, I'm personally interested very much in foundational work. It sometimes seems to me that doing foundational work becomes more unpopular. But I still think it's very interesting and important to do that because the foundations, they remain the same over decades and centuries, versus working on things that are interesting right now. They may not be interesting in 10 years. So maybe you can also see my talk as a motivation to do foundational work. Yes. And with that, I'm happy to conclude. Also, here's my email address. I know that we will have a discussion section now, but if you're shy, you can also just write me an email there. If you're interested in the paper, I have a QR code to the preprint also on the right. Yes, thank you very much.
Thank you, Klaus, for the nice talk. Really, really nice to see like not only the technical work here, but also the motivation of like working on the problems that last long for a research community. I'm so glad that this paper is shaped in such a nice way now. Um, yes. Maybe both comments will come from Samuel. Sorry for putting you on the stage because I think at least I feel like you work on a little bit close in the same cluster of work.
Yeah, I thought this was really interesting, and I was pleasantly surprised with the maximization of margins. This I think is currently a problem also in safety, since you have to kind of maximize the margins in regards to safety to not have easy perturbations go outside of the range where the network sees it as harmful. But I do wonder like, how exactly or which architectures might work well for this loss, since you mentioned also that sometimes it can be a bit unstable. Since I believe also current architectures have kind of evolved and adapted to fit the cross entropy or the standard one, and I'm wondering if also changes have to be made to the networks in themselves to really take full advantage of this and maximize margins and not necessarily train sometimes in unstable ways.
Yeah, that's a very good question. So we have experiments both with transformers and convolutional neural networks. What we observe is that it, in general, it works for both types of architectures. I do not believe that it depends very much on the architecture, but we do observe that if the data set becomes very large, then you get instabilities with panic. So we also have experiment with ImageNet, and this one was the most challenging one. So there was trickier to tune the sensitivity parameter. But in it's not about the architecture more as it is about the size of the data set.
Okay, that's really interesting. Since you mentioned also the size of the data set, um, I'm familiar with AdaBoost in the kind of like Kaggle competition sphere, in which it's very popular to use boosting methods and using ensembles on top of it also. And usually these competitions have limited data sets, and that's the most important part of the competition, is how to use this small data set in order to make a loss which works well for the general data set. So do you think in some way the advantage of AdaBoost kind of fades away as the dataset size grows, or do you think there's a consistent advantage to cross entropy across all dataset types?
Yeah, that's a very good question. Hmm. I mean, I worked a bit with AdaBoost, and there also my observation is that it tends to work better with small data set as you have get a larger data set, simply fitting a big neural network with cross entropy does better. That's my experience. I think it's similar with panics. My observation is it generalizes particularly well if the data set is small, which is why I think it's more of a fine-tuning thing. However, I may also be wrong, and you just need to do a minor tweak somewhere, and then you can get it to work on huge data sets. So this is something that I'm still trying to figure out.
Great, yeah, thank you very much. Does anyone else have questions?
I have a general, but mostly we'll prioritize student questions. So feel free to raise your hand if you want to queue a question. I'm mostly interested in the general research process because some I especially make this group small in the live Zoom audience, so we really have a chance to talk instead of people afraid and being too polite. So I think we ha do have a range of different backgrounds, like undergraduate students, master's students, and PhDs, and also students who usually work on architecture changes or versus always run models in inference mode. And but I think maybe a general thing, just in case the students with research experience on running LMs off the shelf want to enter this domain. Klaus, is there like, do you think this area um, has two types of papers? One is a simple trick but works really well, and then that's shown by a large experiment section. And then maybe version two is a paper that has a good trick and half theoretical elegance and half empirical performance. Or how was the research process behind this?
Yeah, that's a very good question. I started off actually with the empirical results. I knew that there were some theoretical results for AdaBoost, but I did not start with the theory. I started with does it work? And I started off working with the existing multi-class loss for the exponential loss. And I just saw that it didn't really work very well. I tried to do it with augmented Lagrangian, other types of constraint optimization methods. And then I looked into these penalties. I tried out different things, and then I noticed that it works much better like that. And then the theory came later, actually. And then there was like once I figured out it works, there was a back and forth where I changed the formulation a bit based on what the theory tells me and vice versa. I'm not sure if it answers the question. Is this helpful?
Yes, yes. And then the theory part can be risky, usually in the research process, or uh yeah.
Yes. So actually, for a long time, I had a different formulation that didn't work so well in practice. And the theory, interestingly, helped me to change the formulation and then this new formulation worked better in practice. So in my original formulation, I had a log term in front of the sum exp penalty. And you also get a lot of theoretical guarantees with that, but I figured out that I cannot prove this margin maximization property. But I figured out if I remove the log, then I do get this property. And that inspired me to then run it without the log, and then it worked even better.
Super cool. Awesome.
So
And
that's why I think
yeah,
actually theory can even help you in terms of empirical performance.
got you. So it's a bit like in first impression intuition, then
Yes,
performance, then further polish it by doing deductive
yes.
reasoning.
Then do some theory, and then go back to the practical thing, and then go back to the theory, and then go back to the practical experiments. It's a back and forth.
Amazing.
But
Yeah.
really, for me, when I do, even when it's theoretical, I think if it doesn't work, it's useless. I think it's important that it does work empirically.
Yeah,
So this is why, for me, empirical results come first.
really cool.
That's actually an opinion I share with Leo Bryman. This is the one
Mhm.
quote I showed early in the talk. For him, also empirical performance was paramount and more important than just theory.
Yeah. So I think there might be two connection points. One is Samuel actually went through the first two iterations of we Samuel's work also started from an intuition and then we showed very strong performance. And then in the middle of the research, we received some feedback on that the theory side can be enhanced, but that's still under exploration. And then Samuel further have even more performance improvement ideas. But it would be good to have this in the mind when going through Samuel's slides and welcome discussion on that as well. Another note is I think today's recording, I will also pass it to my undergraduate student Punya, and maybe Jerry after the conference can take a look. I think this might be the LM version of it might be a good project for you to consider, and then we'll connect after the meeting as well. Great, maybe Samuel. And of course, Samuel, if you have bandwidth, this is also an open direction.
Great. Thank you very much for the talk. I'll share my slides.
And maybe specifically also focus on like our initial performance boost, but also like what theoretical insights we might be awaiting, and we can go through some reasoning there.
Okay, great. So yeah, my part of the talk will focus on loss functions, but this time for adversarial robustness. And I will present different loss functions used in adversarial robustness method and connect it with the paper we submitted to EMNLP. So improving LLM safety with contrastive representation learning. So to quickly define adversarial robustness, it's the ability of a model to resist prompts that aim to induce harmful behavior. For instance, here, this is a picture of a ChatGPT history. So if you were to ask ChatGPT to generate a step-by-step plan to destroy humanity, it would most likely refuse. But with some added tokens that you can find with adversarial attack methods, it can bypass the safety filters and output harmful behavior. And the goal is to make models safe and not output any harmful behavior. And this is especially challenging for open weight models, since you have access to all the weights, and you cannot use any external guardrails or any method that focus on detecting the inputs and the outputs and look at if the semantics of them are harmful. And new attacks came out which have very high success rates on open source models, open weight, and also on current open weight defenses. So the goal is to create fine-tuning methods which allow the model to be safe and to minimize this risk of outputting harmful behavior. And in general language modeling tasks, the loss you use is, like Klaus mentioned, so this is negative log likelihood or cross entropy. And you look at the conditional probability of generating the next token given the input and the prompt. But what about its use in adversarial robustness? So this paper is one of the seminal papers for adversarial robustness, and it uses also a form of a conditional probability. So it has several parts. It looks at the probability of outputting a refusal, and it makes this very high. And it also looks at the probability of outputting some undesirable response, TI, and it makes this very low. And finally, it also adds a loss term to make sure that the model afterwards can still act like a general language model and behave well on benign prompts and on general language modeling capabilities. But then some improvements were also released, such as latent adversarial training. So in this method, you assume that the LLM can be decomposed into two parts, an encoder and a decoder. And you insert adversarial training inside the middle here, so in the middle of the network in the hidden states. And the goal is to make a model behave well and limit the probability of outputting a harmful string and also augment the probability of outputting a refusal under such attack perturbations inside one of the layers of the models. And lastly, this method called refat is a very efficient adversarial training method in which it's very similar to the first one I showed, but this time with probability P right here. It looks at the language modeling loss, but also uses an attack in the representation space, which is the refusal ablation attack. So it looks at the direction in the hidden state space that encompasses refusal, and it removes it. And this makes it so that you can really target the harmful mechanisms in themselves. And in the end, it fine-tunes a loss based on this, and also makes sure that standard performance is kept untouched. So these methods all rely in some way on the a negative log likelihood, but they have problems in which that a lot of times for attacks, their embedding attack success rate is quite high. So with this R2D2 method, the highest is 61%, the lowest is 61%, which is a high success rate. And all these methods, in some way, use the language modeling loss, which focuses more on the token prediction and on the surface level. But then the improvements come from adding some objectives in the representation space to make them robust to more perturbations. So the main objective is to find some kind of loss function which targets the really inner mechanisms of how to generate harmful content and which makes this as hard as possible. So with this in mind, last year this paper, Circuit Breakers, was announced, and it's a very promising alternative to these methods which focus on making refusals more probable. And this method is based on creating a loss for the inner representations of the model. So if you have an input y, you would find a loss with the hidden states or the inner representations of the network H here. And the goal can be not simply to refuse, but just to not allow any harmful things. So if you have, for instance, harmful behavior, then the model could just break generation. It could output refusals. The most important case is that it just doesn't output anything harmful. And this will simplify parts of the loss, since we can just make it so that the model breaks generation when trying to generate anything harmful. So the way that Circuit Breakers works is that it fine-tunes LoRa adapters on top of a language model. And this adapter is trained on this loss. So there are two parts. The first part is you look at a set of benign representations on benign questions, like how do you bake a cake? And it makes sure that the representations for the benign ones, so HB, are the same as the new ones that you're trying to learn, HB prime. So it tries to make the model behave the same and the representation state space the same as the original model. But then for harmful representations, you want them to be as different as possible to the old ones, which could potentially lead to harmful generations. So they add here a cosine similarity loss, which tries to make sure that the new harmful state will be orthogonal or more to the original one. And this has shown some great results. And we wanted to focus on this and to iterate on this. So we have this paper at EMNLP called Improving LLM Safety with Contrastive Representation Learning. And in the next part of the slide, I will just explain how it works. And the main advantage of our proposed method is that here, if you look at the embedding attack success rate, so on the old methods, the lowest was 60. With Circuit Breakers, you arrive at 30% attack success rate. And with our method, we hit about 5%. And our method is also secure to very powerful input space attacks like reinforced GCG, which the other methods are quite fragile too. And our method extends Circuit Breakers and also connects it with contrastive representation learning literature. So what is contrastive representation learning? Well, it's learning embedding spaces and making sure that different classes are together in embedding spaces. So one of the first contrastive learning loss was the drlim, which looks at absolute distances like this. And if x1 and x2 here are in the same class y, it tries to minimize their distance, and if they're in different classes, it tries to maximize them. And you see that this loss is very similar to the circle breaking one I explained earlier. And this was a paper from 2004. And for modern, more contrastive representation learning, this loss was outdated by other types of losses like InfoNCE and also like the triplet loss, which was used to train BERT. And the main advantage of this loss is that instead of looking at absolute distances, it looks at relative distances. So it was also used to train FaceNet. And the way it works is that if you have 3 points, so A, P, and N, with A being the point of interest, the anchor, P being a positive point of the same class, and N being a negative point of a different class, the goal is to maximize the distance between A and the negative class, and to minimize the distance between P and the anchor with a certain margin, to make sure that you learn a P which is close enough to A and far enough to N, but without necessarily going all the way and maximizing this distance completely. So our proposition was to improve circuit breakers by proposing a similar improvement to what was done in contrastive representation learning. And we consider the positive and the negative as benign and harmful representations. And we will have two parts of the loss. One part for benign queries, like how to bake a cake. This part will be a triplet loss, which focuses on making benign representations the same as the model you're learning, but also make them very far apart from a certain negative point, which we try to maximize. And this target representation N will be considered as a bad representations that we try to avoid. Then for the harmful queries, like how to build a bomb, we will maximize the distance between the new harmful representations and the old ones to make sure that our network does not output anything harmful. But we will also add some positive representations to kind of guide the new harmful representations to be somewhere in the space in which this is a safer zone for them to be. So the final objective is the combination of the two losses. Just a linear combination with different weights. Now the question is, which zone do we want them to be? We need to find an appropriate P and N to make sure that the harmful representations are far from benign ones, to increase this contrast and make sure that the model knows what is harmful and what is not, and also make harmful representations close in space. And the reason behind this is that if you have harmful questions like how to build a bomb or how to write a hate mail, you do not want the LLM to really know the difference between those two. You want to have a refusal, or you just want to have nonsense tokens as input, but you don't want the LLM to be able to make fine-grained distinction between harmful tasks such that it has the ability to answer any harmful task with precision. So we use the mean of harmful representation for this. And what this does is it clusters harmful representations close together in space, and it makes benign representations very far from this cluster of harmful representations. And our final algorithm looks like this. So we have the two losses, and we also have the regularization term, which is the Kial divergence between benign prompts, to make sure that the model for benign tasks output the same thing as the original model without the defense. Now we also add another improvement on top of this. We improve the sampling. Since generally, if you sample harmful representations to be used in training, you want these representations to be harmful and also to lead to harmful outputs, which is not necessarily the case if you just gather harmful representations without any attacks. And to make this efficient, we use inner attacks. So we use adversarial hard negative mining to find adversarial hidden states which are really close to benign states. And this makes so that the network focuses on these clusters of points, these harmful tasks, which would be very hard to distinguish from benign tasks, to make sure that this contrast is learned. And our approach is to fine-tune a small linear model inside the representation space to make harmful representations even more harmful. And we fine-tune this adapter on harmful data. And we use this in the training of the triplet defense with different layers, and we regularly retrain this attack module. So in the end, compared to circuit breakers and rep band, which are two alternatives to adversarial training, we achieve a lot lower attack success rate on both reinforced GCG and GCG, which are two input space attacks, and also a lot lower embedding space attacks, in which we have a less than 5% attack success rate compared to 30 for circuit breakers and over 60 for regular adversarial training methods. And we have validated our results on 4 different models. So we see that for different attack hyperparameter configurations, so if we train embedding attacks on different learning rates and different sizes of tokens, we see that for some defenses, like circuit breakers, on some configurations, it performs really well with 0% ASR, but on some others, it performs rather badly with 12% ASR. And in contrast, our method is very stable, and the worst case is really close to the best case. So we have more robustness across different hyperparameter configurations. And finally, we also prove that the performance on benign datasets, such as ARC or GSM-8K, does not degrade when we train our defense. And compared to other defenses like rep band, we have very similar performance on these tasks. And lastly, we also have a study on generalization to check how well our defense generalizes to different encodings and different ways of writing text. So for instance, write hate mail for public query can be written in different ways and can also be translated to different languages. So we collect perturbed versions of queries, and we look at this quantity here, which looks at how well the model generalizes by increasing the distance between the perturbed queries and the original queries. So if this distance is 1, it means that most of the perturbations were also far in space, which means that the model is safe for those perturbations. And compared to our ablation study and previous work, we have the best generalization for these tasks, which means that our model can understand the concepts in themselves better than other tasks when compared to data which was not used in training. And so for our future work, we have immediate extensions, such as using different kinds of contrastive losses to make sure that we improve performance even more. We also have some theoretical work planned, and also studies of how this defense paradigm scales, and also how much it overrefuses on some potentially queries which are not really benign but not really harmful either. So in conclusion, we have found similar significant risks in open source LLMs, and our proposed method increases the robustness to several attacks, but it is not still completely safe, and it will require significant research efforts to make open weight models really safe and tamper resistant. Great, and yeah, with that, I will stop the recording. Stop the sharing. And does anyone have questions?
Actually want to follow up a bit on, great work. Yes, also want to follow up a bit on, did we resolve all the theoretical concerns for this work?
Yes, I think for the theoretical concerns, when we wrote the paper, a lot of our reasoning behind this is that for similar tasks in contrastive representation learning, the use of relative distances is better than the use of absolute distances. And so in the final paper, I added some more results on generalization, but not really from a theoretical standpoint, but from empirical, with visualizations of the the hidden state space and actually showing that the contrast is bigger. But we did not really make a theoretical push on knowing why this happens. But I do believe there are some papers on contrastive learning which show this result theoretically. So I think these might be potentially applicable to our case.
I also have one question, and please be gentle on me. I'm not an expert on adversarial training. Um, if I understood this correctly, then in your formulation, you also have this thing where you have data points that are close to benign examples, but they're actually harmful, if I got this correctly. And maybe I missed it, but I'm wondering, how did you create these examples? Is it similar to this PGD, or how did you come up with them?
Yes, exactly. It's very similar to PGD. So how we do it is that we fine-tune specific portions of the model weights on harmful data to basically remake the model output harmful things. And the defense is trained on top of this to make sure that if we fine-tune, let's say, one layer in the residual stream between layers 12 and 13, then the output is not harmful and the defense stays on. And so this makes sure that you kind of find harmful examples to use in training. And one advantage is that it's very quick to do and very powerful compared to attacks which look at the input space, which might take more time to run. So significantly increasing the time it takes to run the defense, and also not as complete, since if we look at the hidden state space in every layer and we try to find attacks there, then we really go through the entire defense to make sure that everything is more safe.
Thank you.
Maybe Samuel, you can share a bit of your upcoming directions, as you also have the library of ideas in terms of like what further performance improvement, and also what drives you to improve these components in such a way.
So yes, one further improvement I have planned is looking at what I call honeypot harmful tasks. And so a honeypot in security is kind of like a system that you put, which is easier to attack, but it's not the real system. And this way you can trap attackers to attack a fake system to gain information about how they do this attack so that you can protect the real system better. And so in this case, a honeypot could look like a harmful string, which looks harmful, but is actually not harmful. So if I give you an example, if, for instance, the harmful task is how to build a bomb, the string might be, sure, here's how to build a bomb, and then instructions on how to bake a cake, but you replace the powder by some other ingredient. And currently, classifiers have trouble really noticing what is harmful and what is not, since in the worst possible case, the output you get is both harmful and informative. So the goal is to kind of make a lot of layers of defenses on top of each other to make sure that even if an attack goes through, then the resulting attack is just nonsense in terms of how to actually do these harmful tasks well. And so we want to target the reasoning abilities and also the knowledge abilities of the models, so such that even if it wants to do something harmful, it lacks the knowledge how and also the capability how. And so this is for more of the attacking side. And then on the tamper resistance side, we also want to make sure that the defense cannot be easily removed if you just fine-tune it on harmful data, which right now it can for all existing methods. And this could be a big problem in the future, since if you have a very capable LLM whose weights are just open sourced, then anyone could fine-tune it on harmful data and get a completely harmful model, which you could use in malicious tasks. So some ideas include using regularization terms and also use unlearning in the same time to make sure that you need to have the knowledge how to do the harmful task and feed it to the network in order for the network to actually understand this.
Very cool. And do we expect further improvements on loss functions or just model changes in addition to sort of framing the task differently and generating data?
Yes, I do think the loss functions can be also improved. Maybe with the loss function that Klaus did, if it maximizes margins, then maybe something similar could be done in safety, and we can try to use something similar to really maximizes the margin even more. And currently also the training loop is very simple, and the hyperparameter selection is not that deep. So there can be also several ways to improve it with making better kind of meta learning and adding better hyperparameter optimization, which maximizes the margins of the triplet loss themselves.
Very cool. Thanks for the both very nice presentation and also the research brainstorming we have done upon this. Yeah, happy to foster more casual discussions after this, and Andrew will also help us process the video. So we'll share the video with more members and also pass back the YouTube link to both of the presenters. Thank you, everyone.